Okay, chapter 5, exercise 15. We have 5 different things that are just testing the understanding of how the normal random variable works. Notice that for all 5 of these, the mean is 10 and the variance is 36, which means the standard deviation is 6. So the first thing we would want to do is make sure we convert these to z-scores. So if, for example, the first one is p x greater than 5, and I guess I can probably pull up a notepad here. So we have p x greater than 5. What we want to do is get the z distribution. So another way of writing z is x minus mean minus mu over sigma. So if we're going to subtract mu and divide by sigma over here, we need to do the same on the right side, which would be subtracting the mu, dividing by the sigma. And again, before we write this z, we could have written x minus mu divided by sigma, because that's exactly what we're doing over here on the right side. To get this, then, what we really need is z is less than. That's how our standard normal distribution is defined, if you look in the tables. So we would need 1 minus this here. And this is a, let's see, 5 minus 10, negative 5/6. So we'd have 1 minus like this. And then you can see, because the negative, let me go back here, this right here is the same as 1 minus phi of 5/6. So the 1's cancel out, and we're left with phi of 5/6, which is what they're writing here, 0.833. And then this is just from looking it up on the chart on page, I don't know. It's in section 5.4. Page 190 is where they're getting this number, using this number. On B, you're just going between 4 and 16. So you're, again, from each of those numbers, you'd subtract 10, divide by 6, get that decimal number. Notice the 1 would be a negative, so you have to convert it like we did in part A. C, I'm guessing that's a phi of negative 0.33. Once we subtract 10 from 8 and divide by 6, that would make sense. It's negative 1/3. So this is going to convert to 1 minus phi of positive. And why are we avoiding the negative numbers in here? Just because the chart that we're using is based on the area beyond the mean. In other words, the positive z-scores. So that's why we're converting any negatives to positives. And then we have 1 minus there. Okay, and I think the rest of those are fairly straightforward. Okay, on 17, we have some different bits of information. We know where 2 portions of the normal distribution are, but we don't know mean and we don't know sigma. However, because it's symmetric, we can quickly find out that the mean is halfway in between the two, 180 and 320. So I would just take the mean of those, add them together, divide by 2, and that gives you your 250 for the mean, because we know that 25% is less than 180, 25% is greater than 320. So the average of those is going to give us the overall mean for a symmetric distribution. Now, the standard deviation is a little bit harder. So let's translate the information we have. We know that 25% of the distribution is below. Sorry about that. Okay, so we have 25% of the distribution less than 180. And like we've done before, we can convert that to a z-score because we know that this x minus mu over sigma is the z. We can substitute z in, and we do know the z distribution. So the difference here is now we know that we're looking for 25% of the distribution, and we don't know what our actual z-score is. So when we calculate this in here, we get 0.25 on the chart would give us negative 0.675. Actually, it would give us 0.25 won't show up on the chart at all. 0.75 will, as a z-score of 0.675. But since it's symmetric, we know 25% above, 25% below is going to be the same z-score, just a negative version of it. So that's how we're getting this negative 0.675. Again, we're looking up in the center of the chart. We're looking for 0.75 and then finding out that the z-score is 0.675. So once we know that the z-score is 0.675, then we can set up these two equations right here based on what we found out here. And so we've a couple different ways to approach this, but one is we already know that the mean is 250. So if we plug that in, solve for sigma, in either one, we'll get sigma is 103.7. Once you get sigma and mean, then the rest are straightforward calculations, like in 15, where we're just getting the z-score based on this number. So we would take 200 minus our mean of 250, divide it by our standard deviation of 103.7, and that's what we would then look up on the chart, although because it's negative, we would take 1 minus phi of 0.482 to get that 0.315. And part B is very similar. Okay, number 19. Number 19 is very similar to 17. We have normal random variable with mean 12 and variance 4. As soon as you see that variance 4, you will want to convert to get the standard deviation. So take the square root of that 4 to get 2. And that's where they're getting this 2 from. So calculating the z-score, we'd have whatever the x is, that's what we're looking for, minus 12, that's the mean, divided by standard deviation to get the standard normal here. We want 10% to the right, in other words, 90% to the left. So looking at 0.90 in the middle of the chart on page 190 will give us a z-value of 1.28. Once we have that 1.28, we can set it equal to c minus 12 over 2, or letting x there. It's really not important there which variable you're using. It's just solving for c then to get 14.56. So that's the cutoff point where 10% of the distribution will be higher than that, 90% will be less. Okay, on number 23, we have 1,000 rolls of a fair dice, and we want an approximation that number 6 will appear between 150 and 200 times. So of course this is a binomial distribution. You're either getting the 6 or you're not getting the 6, and we're using a normal distribution to approximate that. If you read the chapter, you'll see that we don't want to hit exactly on the 150 and 200 because it's a discrete distribution where there is actual probability of getting those two numbers, unlike continuous. So to account for that, we just kind of go halfway in between to make sure that we're not getting any of those. This is a correction factor. So instead of 150, we're putting 149.5 instead of 200. We put 200.5. Then at this point, we need subtract the mean. Well, we know that the mean of the expected value of a binomial distribution is just n times p, so 1,000 times 1/6. And we're dividing by standard deviation, square root of npq, and that's what these are here. So we're getting that on both of these. Of course, by subtracting the mean and dividing by sigma, we're converting our x distribution into a z distribution. Then we're taking phi of this minus phi of this. Similar to, this is just the rules of CDF, evaluating it from the beginning to the end point. And once we get that, we get our 0.9258. Now in part B, we have the number 6 appears exactly 200 times, and now we want the probability for 5. Well, I would say the best way to handle this is just to kind of live in that world where there were 200 6s. In other words, now instead of 1,000 rolls, we just have 800 rolls, and instead of the possibility of rolling between 1 and 6, we have the possibility of rolling between 1 and 5. So again, we can apply that correction factor to the 150, and here we have NP, so here's the 800 rolls that are not 6s, 1/5 chance of getting a 5, assuming you don't get a 6. So there's 5 numbers left, all equally likely. The 5 is one of them. And here's our NPQ. Again, our P is 1/5 now instead of 1/6, because 6, we're just ignoring all the cases of 6. When we get Z is less than 0.93, we can't get a negative 0.93 on the chart, but we can get a positive 0.93. So we take 1 minus phi of positive 0.93. Again, anything that has a z-score of negative, look for the positive version of it and then subtract it from 1. Okay, on 25 we have products that are either good or defective or acceptable or non-acceptable, I guess, and 95% of them are acceptable. So probability that at most 10 of the next 150 are unacceptable. Well, of course, we could do a sum on the binomial, letting x range x equal I, where I ranges from 0 to 10, and the p-value there, let's see, 0 to 10, if those are our successes, the p-value would be 0.05. In other words, an unacceptable item would be a success under that definition. We could do that, but that would involve a sum of 11 terms, so we're just going to approximate it with the normal. So the probability that x is less than or equal to 10 equals probability x is less than or equal to 10.5. Notice that we're still in the discrete world here, so these two will be the same because probability will only increase on integers here, so that's why these two statements are the same. The reason we're doing that is the correction factor, so now when we move from discrete to continuous, we have this 10.5 instead of just 10. Okay, and the this is converting to a z right here by subtracting the mean and standard deviation. Again, this is NP, 150 times 0.05. This is our square root of NPQ. Calculating this out to get a z value less than 1.12, it's a positive. We can find it on the chart, 0.8695. And I'm not sure on the chart if they did some kind of interpolation to get a little above 0.112. We could probably check that out real quick. So 1.12 is 0.8686. So if you look it up on the chart, you're going to get 0.8686. What they're doing is adding a little correction factor to that. We're really not concerned with that. That's more of a numerical analysis kind of issue. It is important in practice, but for the purposes of our course, the 0.8686 would be perfectly fine.